Okay, very good. So then let's get started. Today's topic is Reimagine Lab, the future of control systems, system labs, and it consists of two parts. First one will be presented by myself, Alexei, and then um, Armin will pick up from there and deliver the second part, which deals with the recent contribution in this domain. So once again, my name is Alexei, and I'm here today as your host. Senior researcher at Tallinn University of Technology. I also hold a position in the company, which is RA Technologies. Feel free to discover it as well. Very interesting stuff, partly related to what we are going to be discussing here today. And then also IEEE senior member and so on and so on. A few words about our research group as well. So our research group is called Center for Intelligent Systems. Basically, the main topics that we are working on are intelligent control. More recently, intelligent control applied to industrial problems, including the energy sector and so on. However, we are dealing with a bunch of different other topics which all fall nicely into the general developments. For instance, during my doctoral studies, I was actually involved in research related to fractional order calculus, and we're still doing this to this day. Very interesting topic as well, and also partly related to today's discussion. So the agenda is as follows. So we have, let me just put this out here. Agenda is as follows. First, background, then origins of Reimagine Lab, which I think is going to be quite an interesting part, and then also the main part, which is the recent contribution delivered by Armin. Okay, moving on from here, background. So of course, it's essential to discuss the foundational concepts of the present work. And one of those is the so-called idea of digital twins. In our work, we apply the model that was proposed in fairly recent, not too recent, but fairly recent paper by Tao and et al., which is Digital Twin in Industry, State of the Art. This specific digital twins model comprises five main components, which is the so-called physical entity and the virtual entity, which you can see here on this figure. Then we have storage, which is essential because we need to store the data that we collect and thereby also have a capacity to use that for any modeling purposes and so on. We have the connections, obviously, because without those connections, there is no digital twins. It has to be constantly updated to the recent data. And then we have the service layer that is built on top of all of those things. Now, it's a nice model for research purposes, of course, but it's also very practical. And the company that I previously mentioned, which is RA Technologies, in the company, we have applied this very well to solve a specific problem, which is, in that case, control of commercial real estate in terms of indoor climate and some other aspects. So this specific model is highly applicable to real-world problems as well, not only research and things that are related to research. Now, to give a more detailed bird's eye view perspective, digital twins belongs more to the conceptual level of development, so it's kind of high-level modeling. However, in our work, and specifically also with what concerns Reimagine Lab, there's also the part with low-level modeling, which includes mathematical modeling, obviously, for simulation, real-time performance considerations, and all other technical aspects that need to go into the general framework. Another key component that, of course, is foundational for Reimagine Lab is extended reality. Because one thing is that we may have the digital twins as a very useful concept, for research purposes or for practical purposes. But then also, apart from just having the digital twins as some sort of abstract model that we're using, we can also make them come to life. And the way we do this is by allowing users to interact with said digital twins in an extended reality environment. Another thing, of course, to mention here is that XR is a kind of umbrella term, and not every researcher out there agrees that it's a nice term to describe all of these underlying ideas, such as augmented reality, mixed reality, and virtual reality. However, in our work, we do that. We actually say that extended reality is the umbrella term, so please go with that as well. Basically, the idea of Reimagine Lab is we're kind of using either mixed or virtual reality environments to host the specific applications that are tailored to education in control engineering. Obviously, we cannot escape the necessity to address control systems in general, and there's a very nice map which was created by Brian Douglas, which is called the Map of Control Theory. And it lists all of those different aspects of control theory in a nice way. So it's a nice illustration in general. However, for today's discussion, we will limit our attention only to a few key items, which basically are related to feedback and PID control, which probably, if you're joining and you have some experience from control engineering, not necessarily your main or your major field, however, still, those are fairly well-known concepts. PID control is used everywhere to this day, so it should be good enough for following the rest of the discussion. Okay, so now let's jump into Reimagine Lab. Oh, and by the way, just a note for you that if you do have questions, there are two ways that we can handle this situation. So we have quite a few people here in the on-site, and we also have guys joining via Zoom. So Zoom guys, please, if you have questions, definitely you can, again, have two opportunities. You can speak at the end during the Q&A session, or you can just put them into chat so we can address them later as well. But now let's move on to Reimagine Lab. And the key concept is here. The idea is that because of our backgrounds, we're mostly all coming from control engineering domain. And we were experimenting with extended reality at the beginning of 2015. We were looking for good applications of that technology because it demonstrated lots of promise. And we wanted to find the best possible application for it. And eventually, of course, we ended up with control systems because that's our background. And combining the two seemed like a reasonable thing, especially because there's a long-standing problem in control engineering education, which is how do we actually perform a decent number of lab experiments, given the fact that we only have a limited number of devices that the students can use. Hands-on experience is essential in control engineering because, after all, apart from just theoretical developments, we want the students to understand the implications of all of those things. For that reason, we need to be able to scale up efficiently. And we also want for the students to connect the ideas found in control theory to real-world problems. So having those two ideas, key ideas in mind, we wanted to develop a solution that would help solve those issues and also solve a gap in literature. And as part of Dr. Saleh Al-Saleh's doctoral thesis, Dr. Al-Saleh is currently here on site. Hello. So very nice to see you here. This was the framework that was eventually developed. So the framework is fairly general and very useful. And you can also see that the concept of digital twins is used in an excellent way here. So basically, what we offer is a framework that combines several different lab modes into a single solution, which involves hands-on labs, remote labs, and virtual labs. And one example I will show you today as well, well, actually two examples of how this is actually implemented in practice. So we'll not stop here for too long, because you can also scan the following QR codes if you have the time, because I will switch the slide fairly soon. But if you do search for Reimagine Lab MathWorks, for example, or if you search for Reimagine Lab Access, then you will also easily find these publications. So one of them is more scientific, of course, because that was the main point, and the other one is more kind of popular technical side. So you guess which one is which if you want. But basically, the materials are out there, and if you're interested, please have a look. Of course, it also makes sense to go back into history a little bit and show the complete development from where it started and to put the current contribution into context. So it all started with digital twins and extended reality in 2015 for us. At that point, the first experiment with the so-called magnetic levitation system was created. It was a kind of first case for us that we recreated an object as a digital twin, including a mathematical model, which was fairly accurate, and also its virtual, or let's say digital representation, with which users could also interact. And I will show what this means in a few moments. This was our first contribution there. 3 years later, we have actually arrived at a full XR control laboratory. Now, this was done together with our partners from a company which nowadays is called Varcus Solutions. It used to be Limestone Games, but point is that we were able to join forces and create this full solution for a virtual reality lab. And let's have a quick look at what that, how that looked like. So here the idea is that apart from just having access to this virtual plant, let's call it that, with which you can also interact in a meaningful way, just as you would with the real device, we can also, because this is a virtual reality environment, we can also augment it with different additional things like the plot, the time series plot you can see on the left here. So the idea is that we can add many such interactive elements, and because this is a virtual reality environment, there's nothing stopping us from delivering to the user an experience that cannot otherwise be achieved with, let's say, a flat screen approach, because everything can be interacted with, whatever it makes sense to interact with, and you can actually still feel the effective presence, all of these objects when you are in the virtual environment. Like looking right now at a flat screen, it doesn't seem like much, but when you're there, you understand the feeling. So you actually feel like that object is there, and if you know the real life counterpart, it looks and behaves exactly like that. Which means that we successfully achieved one of the key aspects there is we were actually able to perform this, or rather to augment the user's experience or to scale up, because we now had a full lab that could be used without actually interacting with the real devices. Moving on, in 2020, an interesting development also took place. So that at that point in time, my bachelor student Stanislav was working in the lab with a different object, the one you haven't seen before, which is a multi-tank system, another lab scale object that is a replica of some real-life system, which could be considered, for instance, a real-life system analog of that can be found in a water treatment facility or chemical processing. So basically, the idea there was we wanted to introduce tuning controllers into the complete experiment with some novelties. And this is, by the way, the main discussion point for today. But eventually, his work was also turned into a research publication, which netted him first prize at a local competition, state competition for research work, which was a major milestone for us. Then, based on this success, we moved forward with Reimagine Lab. Again, it was mostly a doctoral thesis that made it possible. And in 2020, this was actually, the publication actually was released and the framework was developed. Then, late 2022, HoloLens 2 experiment was created, which is actually quite fascinating. Again, taking the initial idea from Stanislav's work and bringing it to a completely different level, which was noticed also by MathWorks. So in 2023, they invited us to attend or to actually give a keynote at European Control Conference 2023, which was very nice to see as well. A room full of interested people. Some people even didn't get a place there, so it was a really, really humbling experience. And now we arrive to today, and basically today we are going to be discussing further contributions in this domain. But before that, let me also reintroduce the HoloLens 2 experiment to those who have not seen it yet. Basically, the idea, again, you can probably recall the image from before, which had to do with digital twins and the model, the 5-dimensional model of the digital twin. So here you can see a similar architecture once again. Also, if you think about Reimagine Lab, again, a similar idea. So all of those things are somehow related, right? So we have here the multi-tank system, which again is a lab scale model of something you can find in the industry in like maybe in water treatment facilities or chemical processing. We have its digital twin, which combines visualization, interaction, and simulation. And those components are made possible with MATLAB and Simulink software and Unreal Engine. Obviously, in order to experience it, you also need an HMD, which initially, according to the cited paper here, was an HTC Vive with the pass-through. It wasn't very good in terms of the user experience. So then it was later brought into Microsoft HoloLens 2, which is actually a fantastic device. And then from there, we arrived at the following. So this is the experiment that was also successfully introduced into the curriculum, into the course of intelligent control systems. And this is the experiment that the students are asked to perform. Essentially, what you first do is you put the digital twin into the real world. In this case, digital twin means a visualization, which you can also interact with, along with some additional components. Now, obviously, it doesn't really exist in the world. It's a hologram, yes. So here, once it appears, you can interact with it. The idea is that it's connected to a simulation, but you still get to tune the controller, which in this case is a PI controller. So what the idea here is that you have spheres, which you can resize, and the scale of these spheres will determine the coefficients or the gains of the PI controller. And so the idea here was that for students, it might be easier to relate the scale idea to the actual gains and to the effects that they can monitor on the digital twin with the time series plot, which is shown in real time, and then to design a controller that will fulfill time domain specifications. Now, once that is done and the controller is achieved, you can see that now we have switched to real life mode with the actual plant. And that is the major thing here. So first, as a control engineer, it might be a university student or maybe even a control engineer from a company, you get to tune a controller on the simulation. If the simulation is fairly frequently updated with the real system, it should be coherent simulation, which means that the controller you tune for it will also be applicable to the real system, which you can then easily transfer to the real thing. That's the main idea here. And basically, that's actually it from my side. So Armin, please, now it's your turn. So yes, start from here.
So I just want to say again, thank you for coming and thank you for joining online. My name is Armin, and I'm an early stage researcher and PhD candidate here at the Tallinn University of Technology. And since I know that presentation can be a little bit boring and not too engaging, I plan to engage and make it a little bit more interactive. So if you have a phone or want to join online through your computer, you can do so by scanning the QR code or joining at menti.com using that code. You don't have to if you don't want to, but I will give you some time if you plan on doing so. So today I will be talking about our paper that I wrote with Salah, who's in the room, and Alexei, who just presented. titled Assessing Interaction Mechanics in Extended Reality for Control Engineering Applications. Before we start, I just quickly wanted to ask people how familiar they are with XR technologies or digital twins. You don't have to respond, or you can, if you can. Very familiar, okay. Somewhat familiar. So, as you saw in the previous presentation, our background is that this study, control system in extended reality with digital twins, belongs to the domain that is pioneered by Teltech's Center for Intelligent Systems. Here on the picture, you can see on the right the lab scale size replica of a real life system, which you can see on the left is could be used as a water treatment facility multi-tank system. So what was our motivation? We wanted to use tools that are newly used in Teltech courses to mitigate hardware and software limitations shown on the figure above, where I am trying to set the sphere to 2.5, and to address gap in empirical research on interaction methods. Our problem statement was that there's a significant potential for XR technologies to enhance industrial operations through improved human-machine interactions, but existing XR-driven interaction methods with digital twin frameworks lack empirical validation. So, as you can tell, without validation, the optimization of user interfaces for ease of use and technical precision remains fairly uncertain, hindering the effectiveness of XR application in industrial settings. We had three objectives in mind: to evaluate XR interaction methods for the multi-tank control system, to assess cognitive load using the NASA TLX and user experience using the SAS questionnaire, and to provide insight for future XR interface design for control systems. Our methodology consisted of three parts. We conducted a systematic literature review, then we developed and implemented the interaction methods that we wanted to test, and then we performed performance, usability, and workload testing on these interaction methods for control systems. The tools that we used to achieve this were a HoloLens, Microsoft HoloLens 2 headset, Unreal Engine 5, and Microsoft Mixed Reality Toolkit. And also the pre-made system usability scale, or SUS, and the NASA test load index, NASA TLX. First, a quick overview of the levels and interaction methods we chose, and after that, I will introduce them one by one and go a little bit more in depth. We chose two main interaction methods, which were the sliders and the spheres. We had a level with stationary sliders, another level with stationary spheres. We had mobile sliders, mobile spheres, and freeform spheres, just as it was shown in the demonstration on Alexei's video. So, the stationary slider, we had a horizontal and vertical slider anchored in space, which adhered to normal interaction with systems where you have to walk up to the system to interact with it. It did not follow the user. We had a level with stationary spheres, same as the sliders. The PID controllers were anchored in space, and you had to walk up to them to interact with them. The following were the mobile sliders, which were more of a user-centric approach, where it followed the user wherever they went and stayed in their vision to remain within easy reach. Then we had the same thing with spheres, where they remained in reach and they were mobile, so they were following the user's headset position. And lastly, we had the previous implementation where we had the two spheres freeform, fully manipulable. They could be grabbed, relocated, and rotated. However, it's more of a fun way to interact with them. We collected 4 types of data. We collected the test completion time, we collected the test completion if the participants finished or did not finish their tasks, and we collected the system usability scale scores and the nested test load index scores. Here you can see the system usability scale and the nested TLS questionnaire that was used. Some questions that we asked in the usability questionnaire were, for example, I found the method of interaction unnecessarily complex. I found the method of interaction very cumbersome to use. Or in the nested TLX questionnaire, where we mainly focused on the cognitive load of the user, we asked them questions such as, how insecure, discouraged, limited, stressed, or annoyed were you? Or how physically demanding were the tasks? The process of the experiment was as follows. First, we met with the participants, either one by one, or we had two participants at the same time. They were instructed and asked to read and sign the consent forms if they agreed to it. After that, the participants were given a very brief overview and instruction for the experiment. They were not taught how to do the experiment because we wanted to see how they would perform just by themselves. Then they put on the headset. They were asked and instructed to move and start on a random level so we can collect accurate data and not skew our results. Then they were asked to perform two simple tasks per level, and they were timed in their test completion while doing so. After they completed their test, they flipped their visors on their headsets, and they were asked to take a seat at the computer and fill out the nested TLX and SAS questionnaires. And after they'd done this for one level, they repeated steps 3 through 6 until they reached all 5 levels. They done all 5 levels. So regarding the test completion, if they did finish or did not finish, and completion times, which would you think that performed the better out of the 5 interaction methods? The stationary sliders, stationary spheres, mobile sliders, mobile spheres, or freeform spheres?
So we have two opinions.
We have two very different opinions, yes.
The opposite sides.
Well, as you can see, test performance showcased that stationary sliders, which were level 1, were the quickest in completion and the most consistent out of all of them. In the table, you can see the DNF count, which means did not finish. So it only had 2 did not finish accidents where the participant chose to forfeit and not finish the task on it. And we can see that mobile spheres on level 4, which follow the users, were the most challenging with very high variability in completion times and significant did not finish incidents. As you can see, there were 8 people who 8 tasks that were forfeited. Now, regarding the workload, the cognitive workload and the usability of these interaction methods, which were the ones that you think performed better out of the 5? Again, we have a split.
Yeah, but mostly it was about sliders, right?
Yeah. Well, the results showed that if we look at first the blue line in the chart, we can see that stationary sliders on level 1 and mobile sliders on level 3 had the lowest perceived workload, which is the best, and mobile spheres and freeform spheres on level 5 had the highest perceived workload. And when we look at the green graph, the higher is the better there. So we can again see that level 1 with stationary sliders had the highest usability scores, while level 4 with the mobile spheres had the lowest usability scores perceived by the participants. So to to summarize our key findings, we found that the easiest interactions for the users were the stationary sliders, which had the quickest average completion times with only 13.48 seconds. It had the highest usability and lowest perceived workload scores, while the most challenging for participants were the mobile spheres, that had the longest average completion times with around 51.5 seconds, and high variability in performance, lowest usability, and really high workload. So we have 3 key takeaways. The stationary sliders were, as you can tell, intuitive and effective. The spheres needed improvement in usability, and as we can see, the future XR design for control systems should focus on user familiarity and simplicity. Although we had a few study limitations in our case, we had a fairly small sample size given our time constraint, so we only had 30 participants. We had we were limited to specific XR tools and tests in our study, and also it's fair to say that the results may not be generalized to all control systems, as we explored mainly for the multi-10 control system and its PID controller. And thank you for your attention. If you want to connect or read the paper, scan the QR code, and I have a question time.